Hi class, this is Neil and this is lesson 7 on average rate of change. So getting right into it, in the do now, we're asked which of the following is the correct formula for the slope of a line. So remember, slope is the same thing as the rise over the run. Another way we think about it is the change in the y value, so the difference in the y over the change in the x values. Well, if I look at my choices, here I'm seeing a difference in x on top, so no way. Here I'm seeing a y2 minus an x2, so it's a difference of a y and an x, no way. 3 is our correct answer. We're seeing a change in y over a change in x, or a difference in y over a difference in x. Choice 4 is not correct. That's the slope-intercept form of the line, which you've seen before and we'll revisit a bit in Algebra 2. All right, question 2. Determine the slope of a line that passes through the point 13, -4 and 17, 6. Well, going back to that formula we just saw, we've got m equals y2 minus y1 over x2 minus x1. Here are my 2 points. Now, it doesn't matter what I label. I'm going to label this x1, y1, x2, y2. All right, so plug in those numbers into that formula. I'll have 6 take away -4 over 17 take away 13. All right, subtracting those 6 take away -4 really becomes 6 plus 4. Subtracting a negative, you change the sign to positive. 17 minus 13 is 4. This becomes 10 over 4, or 5 over 2 as my slope. So for every 5 we go up, we go 2 over. All right, moving on to the lesson. So let's look at the problem. It says the function g of x is graphed below. Determine the average rate of change of g of x on the interval 4 is less than or equal to x, which is less than or equal to 13. Okay, so what do we notice about this graph? What are some things we notice? Well, one thing I notice is that this is a curved graph. It's not a straight line. So that means if I were to talk about the slope here relative to the slope here, what do you notice? Well, one thing I notice is that the red lines where I indicated the slope of that curve is much steeper than the blue. So the slope is not constant, or it's not the same. We're not dealing with a straight line here. We're dealing with a curved line. So the slope will be changing depending where on that curve we are. Now, what we can talk about when we talk about a curved line is not the slope, but it's really the average rate of change. So how is that line changing between certain x values? So let's take a look at it in the context of this problem. So here I've got determine the average rate of change on the interval 4 is less than or equal to x, which is less than or equal to 13. So that really means between when x equals 4, which is here, so that's that point on the curve where x equals 4, and where x equals 13, this is where x equals 13. So that's the point on the curve there. So if I'm interested in the average rate of change on that interval, the way I can think about that is what is the slope of the line that connects those 2 points? Because that's on average how that curve is changing between 4 and 13. All right, so really 2 ways we can do this here because we do have a graph. So we know that slope is the same thing as rise over run. So if I just look at this at these 2 points and I count the rise and the run, my rise is 1, 2, 3, 4, 5, 6, 8. So my rise is 8. My run is between 4 and 13. So that's 6 and 3, which is 9. So 8 over 9 would be my slope. Now, remember, here we're not talking really about the slope, but we're talking about the average rate of change. But they're calculated in the same way. If I were to do this using the slope formula, what I would need to find is the values of the points. So at 4, my y value is 7. And at 13, my y value is 15. Okay, a lot of counting there, but we got it. So, all right, the change in the y's. So that would be 15. Take away 7. So y2, y1, x1, x2 over 13 minus 4. Let's hope we get the same thing, and we do. All right, so average rate of change is the same thing as, really, a way we can think of it as the slope between 2 points on a curve. If I were to connect a line between those 2 points and find the slope of that line, that's the average rate of change. Remember, we find that y2 minus y1 over x2 minus x1. All right, so let's take a look at this in a different problem. All right, so here we have the following data shows some information about the number of new COVID-19 cases in New York City during March 2020. C of t for various days since the outbreak began. And t is the time the outbreak began. T equals 0 corresponds to 2/29/2020 when there was the first case in New York City. What was the average rate of change between day 15 and 25? So one thing you notice here in this table, or one thing I notice, is that we're not going up really by the same amount each time. So between day 0 and 15, we go up 1,036. So an increase of 1,000. Between 15 and 20, we go up another 3,000. So 5 more days, another 3,000. 5 more days after that, it's only going up 800. All right, so what I can see is we're not changing by the same amount each time. All right, so what I'm asked is, what was the average rate of change between day 15 and day 25? Okay, so what I'm interested on in this table is this data point and this data point. Now notice, if we think about this in terms of slope, it's really our y value, that's our x value. All right, so this will be my, let's just say y1, y2. This will be my x1, x2. Okay, because we said average rate of change is the same as slope, we're just going to plug our information into this formula. So m equals 4,874 minus 1,036 over 25 minus 15. Okay, so I'm going to need to pull out a calculator for that because I don't want to do that subtraction by hand. All right, so we get 3,838 over 10. Now if I divide that by 10, I'll get 383.8. Okay, so what does that mean in the context of that problem? So what that means is the average rate of change. Let me actually do this in a different color because we want to a lot of times with these problems, we want to write it out in a sentence so we can kind of understand what that number means. So the average rate of change in the number of new COVID cases in New York City between day 15 and 25 was 383.8 cases. All right, so that's what that means in the context of this problem. Okay, I don't believe we did question 3 in today's lesson. We did look at question 1. So which of the following is the average rate of change of g of x on the interval -5 to 7? All right, so -5. These are x values. So here's my first x value of -5. My x value of 7 is here. Okay, so I can write out those points. So -5, -3. This is the point 7, 3. All right, now remember I said there's 2 ways we can find this if we have a graph, and the graph is nice and neat like this one. So I'm going to connect those 2 lines, or sorry, those 2 points, and I'm interested in what is the rise compared to the run on that interval. That's the same as the slope. So 1, 2, 3, 4, 5, 6. So the rise is 6, the run is 12. So that simplifies to 1/2. If you wanted to do that with the numbers we have, we're going to label x1, y1, x2, y2. So 3 take away -3 over 7 take away -5. So we get the same thing, 6 over 12, which is equal to 1/2. All right, so number 3. We actually don't have a lot of space for this, but that's okay. All right, so for question 3, we're told that the distance needed to stop a car after applying the brakes varies directly with the square of the car's speed. The table below shows stopping distances for various speeds. All right, so I mean, basically what that means, it's like kind of complicated language. I mean, one thing you notice is that as the speed increases, so as we go up in speed, the amount of time it takes, or the amount of distance rather, that it takes for your car to stop increases. So if you're going 30 miles per hour, the amount of distance it takes for your car to stop is 56 feet about. But if you're going just 10 more miles above that, so 40 miles an hour, it takes 100 feet for your car to stop. All right, so what we're interested in says determine the average rate of change in braking distance in feet per mile per hour, so kind of a crazy unit, but that's all right, between one car traveling 50 miles per hour and one traveling 70 miles per hour. And explain what this rate of change means as it relates to braking distance. All right, so we're finding average rate of change here. Sometimes I like to shorten that to AROC because I don't want to write all that. And we know that's the same as the slope. And we're interested in it between 50 miles per hour and 70 miles per hour. So here's 50 on my table, here's 70. These are really, you want to think of the top row as your x values, the bottom row as your y values. So our slope there is going to be 306.25 minus 156.25 over 70 take away 50. All right, so turn to your calculator, 306.25. Take away 156.25. All right, that gives you 150 over 20. If I simplify that, it simplifies to 7.5. Now, what's our unit there? It's right here, feet per mile per hour. Okay, what does this change mean as it relates to the braking as it relates to the braking distance? Okay, so let's just kind of take what we have in the problem, what's explained in the problem, and rephrase that as a sentence. So what this means is that the average rate of change in braking distance between, and I'm going to include this part here, between cars traveling 50 and 70 miles per hour. Oh, sorry. Is, and now I'm just going to include my numbers, 7.5 feet per mile per hour. All right, and that was it for today's lesson.